Let's consider the following. We have our function f of x, y, z, and it's a function obviously of three independent variables. We have our points 4, -1, and 1, and the unit vector 0, 4/5, and -3/5. And what we want to do is find the gradient of our function, and we also want to evaluate the gradient at the point P. So let's do that. So our function f of x, y, z is equal to x squared y c minus x, y, z to the fifth. Finding the partial derivatives is necessary in order to find the gradient, because the gradient of our function at x, y, z is just equal to the composition of all partial derivatives. So it's partial derivative with respect to x, with respect to y, and with respect to z. So let's find the partial derivative with respect to x. That is treating y and z as a constant. So we have y, z, 2x minus y, z to the fifth, which is of course 2x, y, z minus y, z to the fifth, which is the partial derivative with respect to x. Partial derivative with respect to y of our function is treating x and z as a constant. So we have x squared z minus xc to the fifth, and then the partial derivative of z is treating y and x as a constant, so it's x squared y minus 5xyz to the fourth. That's pretty much it. So the gradient, x, y, z, composition, so we have 2x, y, z minus y, z to the fifth, x squared, z minus x, z to the fifth, comma, x squared. I need some room here, so I'm gonna delete a lot of this. Whoops. X squared y minus 5xyz to the fourth. Let's evaluate the gradient at our point. So the gradient at the point 4, -1, 1 is, it's not too hard to do. We just have to evaluate. So it's just 4. I need to get some more room. I'll do it down here. So gradient 4, -1, 1. We have 2 times 4 times -1 times 1 minus -1 times 1 to the fifth, comma, 4 squared times 1 minus 4 times 1 to the fifth minus, so it's a lot of algebra, or arithmetic, I should say, 4 squared minus 1 minus 5 times 4. Very easy to mess up, so try to be a little careful. I'm gonna double check after I'm done with this. Okay, let's see. 2, 4, -1, 1 minus -1, 1, comma, 4, 1 minus 4, 1, okay, 4, -1 minus 5, 4, -1, 1. Okay, that's good. Alright, so I'm going to try to do this all at once. So this is going to be 8 minus 8, and then 1, so it's plus 1. Okay, so this is just minus 7. This is 16 minus 4, which is 12. And then this is minus 16 plus 20, I think. See, yeah, that's correct, which is positive 4. So this is our answer as our gradient at 4, negative 1, 1. So negative 7, 12, 4. And then we want to find the directional derivative. So it's just going to be directional derivative in the direction of our vector u of our function f at x, y, z is the gradient at x, y, z, which is a vector, by the way, dot product with the unit vector. Is this a unit vector or is it not? Well, we can determine that by taking its magnitude. So square root of 0 squared, which is 0, plus 16 25ths, plus 9 25ths is indeed 1. Just some quick arithmetic. There you go. So we can find this quite easily. So at the point 4, negative 1, 1 is just equal to the gradient, which is negative 7, 12, 4, if I did my work correctly. And then we have 0, 4/5, negative 3/5. If I didn't do my work correctly, you wouldn't be seeing this video. So 4, negative 1, 1. So you most likely wouldn't be seeing this video if I didn't do my work correctly. Unless I miss it, which I most likely will not. So this is negative 3/5. Okay, so this is just a dot product. We have 0, we have 48/5 minus 12/5, 36/5. We can't really simplify, so this is our answer. So rate of change, so we have du f at the point 4, negative 1, 1. (36/5). And that's our answer. We're done.